Hello everyone, welcome to lecture 23 on Mechanics and Materials 1. In this lecture, we want to talk about energy methods. In particular, we cover sections 14.1 to 14.3, 14.5, and 14.6 of chapter 14 of the Hibbeler book. So as we mentioned, we want to talk about energy methods, and in order to do that, we need to speak about external energies and internal energies. In particular, we need to explain the similarities and differences between these two energies. In order to do that, I start with a very simple example, possibly the simplest example in the topic here. You can think of a spring. It's fixed on the wall on the left-hand side. It has a spring constant K, and you apply a force F to the spring, and also you can imagine it would change its length as much as delta. So delta is the change of length. Now for this problem, if we want to talk about the internal energy, we also call this stored energy or strain energy. If you want to talk about this internal energy, and we show it by UI, the subscript I stands for internal. The relation for that, if you remember from your previous courses, it would be 1/2 times K spring stiffness times delta squared. So that's your relationship for internal energy. Now, obviously, in the description of the internal energy, you do not see specifically the force that you apply. So the force here is applied by a user, and then this is in principle an external quantity on the system. So from that perspective, then, if we want to include force, or the force F here, if we want to include that in the picture, we need to talk about the external energy, or otherwise work. We use the same letter U with subscript E now, standing for external. Now, if you think of this example, you can imagine that at any distance delta, or change of length delta, the force itself is F. And the relationship between the external force and displacement is linear. So if you remember F equals K delta, basically that would tell you that. So basically what I'm trying to tell you is that the force displacement relationship would be the line here. So this is force displacement relationship function, and the integral of that line, or the area before that line, that would be the external energy. So that external energy is then 1/2 times F times delta. This is the area of the triangle. So you can imagine that if you assume F equals K delta, which you could otherwise see by the equilibrium of forces here, then UE and UI would be identical. So if you insert F equals K delta, UE would also be 1/2 of K delta squared. And that would give you the balance of energy, or conservation of energy. So what I'm trying to say in this example is that the right-hand side and the left-hand side of the green equation that you see here, they are very, very similar conceptually, but also they are different. The right-hand side F equals K delta, that is equilibrium of forces. So that basically tells you if you cut a little piece here, so if you use method of sections like we did before, on the right hand side you would have, let's say, F, on the left hand side you would have K delta from the spring. So on that portion, if you want to have equilibrium, the relation F equals K delta must hold. So from that relation you can see that the energy UE, or external energy, equals UI. So the conservation of energy holds. But also alternatively, you can imagine that if you assume that you have the conservation of energy already, from that you can conclude that the forces are in equilibrium. So again, if you look at these two, they are different in the sense that here you talk about forces, here you talk about energy. But as soon as you assume one of them holds, you can conclude the other one holds. So each of them would also imply the other one. All right, so this is essentially the discussion and understanding about external and internal energy. But obviously, we are not only limited to a simple case like a spring here, we want to extend this discussion now a little more. But the big picture is here. The big picture is that until now, we talked about equilibrium of forces. But in this lecture, we want to talk about conservation of energy as an alternative approach or as an alternative view for mechanical problems. Now, if we are not talking about a spring, what would be the internal energy? How do we define internal energy or strain energy if the problem is not just a spring? As you can imagine, strain energy or stored energy or internal energy, it should depend on internal arguments, on internal quantities. And you can imagine the internal quantities inside a beam or a shaft, they are stress and strain. So if you find stress strain contraction, and basically that means some sort of multiplication of stress and strain, then you can obtain the strain energy. So if you have a problem like axial loading, your stress would be a normal stress, your strain would be normal strain. So if you multiply them, you get something like energy. If it's a torsion problem, then your stress would be something like shear stress, your strain would be shear strain. Again, if you multiply them, you get something which has the dimension of the energy at least, or the flavor of energy. So that would be your strain energy. Now, how about external work, external energy? Also, you can imagine that our typical or our generic definition of work must hold. So work or energy is force times deformation. That means you need to have a contraction, or then again some sort of multiplication between load and deformation to calculate energy, external energy in this case, or work. Again, if you are dealing with an axial loading problem, usually you apply a force F and delta is the displacement or deformation measure. If it's a torsion problem, your external loading would be torque, and then your deformation measure would be angle of twist. If you're thinking about bending, assuming that you apply a moment M, then your deformation measure is angle of theta. So in this picture, for simplicity, we neglect transverse shear. We can argue transverse shear has less effect in this picture or is less significant, and then for simplicity, we just avoid transverse shear, but otherwise it's not really complicated either. If it's transverse shear, then your force would be shear force, and your sort of deflection or deformation in the same direction would be the corresponding deformation measure. Okay, so this is what we want to do. For different problems that we have looked in this course so far, so for axial loading, torsion, and bending, we want to do this exercise. We want to calculate the external energy, and we want to calculate the internal energy for each of them and see if they are equal or not. This is what we want to do. Next, before we do that, we need to do two things. The first thing is that I should remind you that conservation of energy that we talk about here is exactly the first law of thermodynamics. Okay, so in the context of a mechanical course or structural mechanics here, we just call it conservation of energy for simplicity, but you can argue this is exactly the first law of thermodynamics. And another relevant note to that is that we talk about elasticity. So elasticity means that there is no dissipation. There is no dissipation of energy. Okay, so in this course, from time to time, we also talked about plasticity, but this picture and what we do today, it does not include plasticity in principle unless we introduce it into the framework, which makes it very complicated. But the equation that we are working with, it's only valid for elasticity so far. So in order to calculate the strain energy in general, we begin with a particular example. So assume you have the following case. You have an incremental piece of material, let's say it has the volume dV with the dimensions dx, dy, dz, and you apply a normal stress sigma z. Now for this picture, if you draw the stress strain diagram, and then again, I emphasize that we are talking about elasticity, stress strain diagram is just a line. So you have the linear relationship sigma equals E epsilon. Now the area under the line, or the integral here, this would be 1/2 of sigma times epsilon. But if you look at that area, its dimension is Newton per meter squared. Again, remember epsilon is dimensionless, so you can imagine it's meter over meter, so it's dimensionless in total. And stress is Newton per meter squared, so it's Pascal basically. But alternatively, you can think that Newton per meter squared can also be expressed as Newton meter over meter cubed. Now, this is interesting because this basically tells you Newton meter is energy and meter cube is volume. So this basically tells you that the area is energy density. It's the density of energy. So it's energy per volume, and that's the energy density. All right, so the area under the line, or 1/2 of sigma epsilon, is internal energy density or strain energy density. So if we have the density of this strain energy and we want to calculate the strain energy itself, all we have to do is to integrate this over the body. So strain energy Ui is integral over volume of strain energy density, which is the area, 1/2 of sigma epsilon. Now, if you remember sigma equals E epsilon, so using this relation, you can also express this as 1/2 of E epsilon squared and 1/2 of sigma squared E, integral of them over the volume. All right, so this is our strain energy for a simple case like this. Now we can ask ourselves, well, it's good, but this is only for normal stress-strain relationship. How about a shear problem? So if you look at the shear problem, like this one now, you can play exactly the same game. So you draw the diagram, stress-strain diagram, but now it's for shear stress, shear strain. But then again, the same idea holds. If you calculate the area here under a stress strain, that would be your internal energy density. And in order to calculate the energy itself, all you have to do is to integrate that over the volume. And then again, using the relation tau equals g gamma, you can write it in its, let's say, in its original form, which is 1/2 of tau gamma, or you can write it as 1/2 of g gamma squared, or 1/2 of tau squared divided by g. All right, so now we know how to handle a case that is normal stress and shear stress. So if I summarize these two, we have these two pictures so far. The first one is for a normal stress. The second line is for a shear stress case. But then again, we can ask ourselves what happens if we have a multi-axial stress state. So you can have normal stresses in every direction and shear stresses in every direction. What would you do then? It's exactly the same thing as we did before. It's more like using superposition, because you can calculate these energies and you just add them together. So for a multi-axial stress state, this is what's going to happen. Your internal energy would be the sum of all the energies due to normal stress-strain relationships and all the energies due to, let's say, shear stress-strain relationships. So 1/2 of sigma x epsilon x plus 1/2 of sigma y epsilon y plus 1/2 of sigma z epsilon z. So these are for the normal stress strains. And then for the tangential ones, you have 1/2 of tau xy gamma xy plus 1/2 tau xz gamma xz plus 1/2 tau yz gamma yz. And then again, you remember that tau xy and gamma xy, they are symmetric. So that symmetry is something you should not forget. So basically, it's already inherently here. All right, so this is strain energy. Now we know how to handle strain energy, how to calculate strain energy. For external work, we already know what to do. So if you want to calculate external work, either you are talking about axial loading problem or torsion or bending. And then for each case, you would calculate force times this, or load times displacement, or load times deformation, basically deformation measure for that case. Now, that deformation may be displacement in case of axial loading, or it may be angle if it's torsion or bending. So this could be displacement, or it could be just change of angle. And load could be force, or it could be moment. All right, so we know how to calculate now strain energy, UI, and external energy, UE. What we want to do next is to see what comes out of setting these two being equal. So what happens as the consequence of UI equals UE? This is what we want to do. And in order to do that, we want to specifically go through these three cases. All right, as always, we start with axial loading. So you have a shaft here with a normal force P at the end. The stress in the shaft is calculated via the relation sigma equals P over A. And if you draw the load displacement diagram, load or force is P here, the formation is actually displacement along the main axis, delta. So the work would be 1/2 of P delta. Now, if you remember for this case, it's a normal strain case. So we just mentioned that the internal energy would be integral over the volume 1/2 of sigma squared divided by E dV. Or again, in its original form, it's 1/2 of sigma epsilon dV. And that would have been the area below the sigma epsilon curve. So we want to do exactly that. This is now your external energy UE. This is the internal energy UI. And we set them to be equal. We want to know what would be the consequence of that. So in this relation, instead of sigma, we are going to use the relationship between stress and force, which is P over A. And if you do that, you will see the next line. Now, you would have A squared here that you can cancel with A. And pay attention that instead of dV here, we have written A dx, and then we have integrated over the length L. So when you carry out that integration, what you will see is that you get 1/2 of P squared, so there is power 2, L divided by EA. Now, if you cancel 1/2 from left and right, and then you cancel P with 1 power of P here, what you will see is delta equals PL over EA. Now, if you remember, this was our key relation for axial loading. So basically, if you impose the energy conservation in axial loading problem, you can prove the relation delta equals PL over EA. Now we are going to repeat the same thing or play the same game again for a torsion problem. So imagine now you have a shaft here, you apply a torque T, and you have an angle of twist. So the relationship between stress and torque, you remember it was tau equals TR over J. J was polar moment of inertia, R was the radius of the shaft. I'm showing the shaft being rectangular here, but obviously it should be circular according to what we have learned. All right, so we have the energy, we have the relationship between stress, shear stress, and torque, T. And the external energy, or then again, the work that you apply is 1/2 of T times phi, where T is torque and phi is angle of twist. So by setting these two equal, you would have 1/2 of T times phi equals integral over volume of 1/2 times tau squared divided by G an integral of that over the volume, as I mentioned. So the next thing you want to do is to insert the relation that we had here for the shear stress tau. But also, in order to find something more similar to what we already know, we write dV as, let's say, dA dx, or in particular, if you have integral of something over dV, we write it as integral over length and then integral over area of that thing dA dx. So this is basically what we do. Now, if you do that, you will see that you have a term which has r squared dA. So the rest of the terms you have here, they are not depending on the radius, or they are not changing in an area. So if you take this out, you would have an integral over a of r squared dx. And that thing is exactly the polar moment of inertia, J. Therefore, you can see that this expression that we have here, again, canceling a power of J here and there, you can see the expression would lead to 1/2 of T squared L divided by GJ. And then again, if you cancel 1/2 from left and right, you cancel torque and one of its power here, you would end up with the relationship phi equals TL over GJ, which again is one of the key relations that we learned and we calculated throughout the semester previously. So I hope this sort of exercise, it makes it clear that setting internal and external energy being equal, it gives us our missing relation for the deformation. That again, previously we calculated these through equilibrium of forces, obviously. So it was also possible to derive these relations. But now the starting point is not equilibrium of forces. Our starting point is conservation of energy. So this is exactly conservation of energy. This is external energy, this is internal energy. Now again, you can play the same game for a bending problem. For a bending problem, the relation between stress and moment is given here. So sigma equals my over I, assuming that you have a bending like this. So let's say the bending is with respect to maybe z axis, and then I would be with respect to z axis, and y is the distance from the z axis. So this would be your stress relationship with moment m. Again, the minus is just to give you the sign correctly. And if you think of the external work, if the beam deforms by angle theta, that moment times angle, this would be your energy, or 1/2 of that, because you would integrate. It's very similar to what you had here. So again, you can imagine if you have a torque times change of angle is the work, or incremental work. Now if you have a moment, that moment times change of angle would be your incremental work, and if you integrate it, you would have 1/2 of m theta. Now, similar to what we had done previously, you would equate the external energy to internal energy. And you pay attention, the internal energy is exactly what we had in the previous case for axial loading. So the equations are the same, but the relationship between stress and the external load are different. So now here, this is your relation for stress. What we do next is to write, again, the integral over dV as double integral over dA dx. And if you take out the integral, which looks like y squared dA over A, you would take out the moment of inertia I, as you can see here, and that I would be cancelled with one of the powers of I in the denominator. So you would have this relation. And then again, you can cancel 1/2 from here and there. You can cancel m with 1 power here. And then you would end up with the relation theta equals ml over ei, which we have also seen before. Okay, so this is everything I wanted to tell you about using the equilibrium or the conservation of energy. So if you say ui equals ue, from that you can derive new equations in each case, which also previously throughout the course we had seen them, but we had seen them or we obtained them through equilibrium of forces. But this is very interesting to see that in a few lines basically you can calculate those complicated relationships that we calculated previously. So what we do next is to have an exercise together and use this in a more concrete example. Exercise 1 in this lecture is similar to problem 14.5 on page 732 of the book. For the shaft shown in the figure, compute the strain energy and external work. Assume G and J as given constants. So we have a shaft here. It's fixed in the wall, let's say at point C. We may call this point B and this point A with the given dimensions. And you have the external torques 40 and 55. Assuming that G and J are given and constant throughout the shaft, you are asked to calculate the internal energy and external energy. So this is basically our shaft, and if we draw a one-dimensional picture of it, you can imagine it's like this, assuming that our plus direction would be towards left as is shown here. Then the torque here would be minus 40, or the internal torque from A to B would be naturally then minus 40. And what you have here is in the opposite direction, so it's plus 55, again, as assuming that this relation would be your plus, you would have this 40 would be basically minus 40, this 55 is plus 55, as you can see by the directions shown here. So consequently, between A and B, the internal torque would be minus 40, and between B and C, the internal torque would be plus 15. Now, in order to calculate the internal energy, remember this is our relationship. And then again, this relationship is just a direct consequence of what we had before. It's usually tau times gamma dV. But then because gamma is tau divided by G, you can write it like this. And then again, 1/2 of tau gamma is nothing but the area before or below shear stress strain diagram. Okay, so this is your internal energy formula. And because your shaft is made of 2 parts, in order to calculate this integral over the volume, we would just write it as a sum over the two parts. So for each part, you calculate T within that portion. You calculate L, and G and J, you have them. So G and J are constant. We just write them as they are. 1/2 is just 1/2. Now, from A to B, T is minus 40. From B to C, T is plus 15. So that's what it is. And this is the length AB, and this is the length BC. All right, so nothing is super complicated here, really. Your internal energy is 633.75 over GJ. This is the internal energy, the first part of the question. Now, what we want to do next is to calculate the external energy, UE. Again, the external energy now is the energy here at point A and the energy at point B. For each of them, the energy would be 1/2 of T times phi. So again, the energy due to torsion is 1/2 of torque times angle of twist. And this is equivalent to force times displacement, obviously. Now, at point A, the angle of twist at point A, you can write it phi A equals phi A with respect to B plus phi B with respect to C. At point B, the angle of twist is just phi B with respect to C. And then you can imagine for each of these, you may want to just add the angle at C, but the angle at C itself is just 0 because it's fixed. Now, for each portion or for each part of these angles that we have here, we use the relationship for angle of twist that we have learned before. Phi equals TL over GJ. So from A to B, you would use torque from A to B times length of AB divided by GJ. From B to C, TBC torque, again, length of BC divided by GJ. And if you add them up, you get minus 25.5 divided by GJ. And then again, for BC here, you would have 4.5 divided by GJ. All right, so now you have the formula for external energy. In this formula, you didn't know what was the angle of twist, and now we calculated these two angles of twist from the parameters that we had already. Now, all you need to do is to insert those into the relation that you have for the external energy. That would be 1/2 times minus 40 times angle of twist. Again, this is TA. And now here you have TB, it's 55. So pay attention. Here you talk about TB itself, which is 55, and it's plus 55 as we discussed. Previously, when you use this formula, the T that you have here is T is the internal torque from B to C, which was 15. Okay, so there is a difference. Pay attention to that. And if you calculate this, the external energy ends up being also 633.75 divided by GJ. And if you compare the two, you can clearly see that the internal and external energy are equal. Okay, so this was basically everything for this example. Now, what we want to do next is to go beyond this. In this example, we showed that we can calculate this, and we can calculate this one, and we can prove that they are equal. This is what we did. What we want to do next is to do kind of the opposite. We want to assume that they are equal and see if from setting them being equal, we can calculate something which otherwise would be difficult to calculate. So this is what we want to do. And then again, we can do this for any of these cases. So whether you have axial loading, torsion, or bending, the strategy that we are going to introduce is exactly the same thing. Having the information that you have here, we can show that for any example, the energy conservation holds. However, what we want to do next is to employ this relation as a starting point. So we use this as our point of departure, and we use that to compute deformation, for example. In particular, we do that for the case of truss structures. Exercise 2 of this lecture is similar to problem 1411 on page 762 of the book. Determine the vertical displacement of joint B of the truss structure shown in the figure. The cross-sectional area of each member is 400 millimeters squared, and Young's modulus is 200 gigapascal. So you have a truss structure given in the figure. You apply a force of 100 kilonewton downwards at point B, and we want to know, due to that force, how much deflection you would get at point B. So in order to solve this problem, we use the conservation of energy by setting the external energy equal to internal energy. Now, the external energy, if you have a deflection of VB at point B and you apply a force of FB, you can imagine the external energy, or the work that you have to do here, is 1/2 times force times deflection. The internal energy, on the other hand, is the sum of the internal energies of all the members. So the external energy here is 1/2 of FB times VB, as we just discussed, and then VB is displacement at B in the same direction as force FB. That would be equal to sum of the internal energies in each member, and for each member the internal energy is 1/2 times F times delta. So for each member you have a force F in the member and the displacement of that member, or change of length of that member rather, and that change of length delta is FL over EA. So that's all you have to do, and then if you just cancel the 1/2 on both sides, you will come with this relation. So it would be FB VB equals sum over all the members, F squared times length divided by Young's modulus times area. The only remaining step really is to calculate the F's. So in order to calculate the F's, you can use the method of joints, for instance, or method of sections, it doesn't matter, but you would need to calculate the forces in each member. And if you do that, you would have these numbers that are shown here. And then again, minus means compression, plus means tension in that member. Okay, at this point, basically, we have already solved the problem. All you need to do is to insert these values into the equation, and then you would have one equation, one unknown, and you can calculate the deflection at point B. In order to do that more clearly, we use this table here. So we write a table. At each row, we write a different member. So you would have AB on the first row, then BC, second row, AC, third row, and CD on the last row. And then for each of the members, we write the internal force F, its length, area, Young's modulus, and then the relation that we have here. So F squared times L divided by EA for that particular member. Also, I am writing the units to be careful. So if you fill out the table, and it's a fairly simple table because all the members are made from the same material, so they all have E equals 200 gigapascal. They all have the same cross-sectional area. The lengths are not identical, but you can calculate them. So this one is 4, this is 2, and this one is 2. And these are 2 times the square root of 2 each. And the forces are as we have calculated them. So eventually, you would calculate what you have as internal energies for each member. And if you add them up, you would have 2,915. And this 2,915 is equal FB times VB. FB itself is 100 kilonewton, which tells you VB, the change of height or deflection at point B, must be 29.15 millimeters. Now, pay attention, this is millimeters because we used kilonewton here. In other words, the unit here was Newton meter. So if you use kilonewton, then you basically calculate millimeters. All right, so this is what you had to do. We wanted to calculate the deflection at point B, and we have it. It's 29.15 millimeters. And as you can see, everything that we have done is on this slide already. So we started from the conservation of energy. So the conservation of energy is our point of departure. And then through the steps that we have here, we ended up with the deflection at point B. So this was the answer to this question. However, this question was a lucky question, or the task we had to do was a simple task because for the given picture, we asked you exactly to calculate the deflection at point B where you applied a force in the same direction. However, what if I asked you to calculate the deflection of point B, or the change of coordinate of point B in the horizontal direction? So what would that be? Or what if I ask you to calculate V at point C, or any other point, or in any other direction? So how do we do that if the point and direction that we want is not exactly the point and direction where we applied the force? This is what we want to do next, and that brings us to the so-called the method of virtual forces. Okay, so this is the summary of method of virtual forces. The idea here is you would have a real system where you have real loads. So you would have your real system, And then you define a virtual system. On that virtual system, you apply a virtual load, and we usually apply a unit load 1 for simplicity. On that virtual system, you apply a virtual load, again, usually unit load for simplicity, but it doesn't have to be 1, exactly at the point and the direction that we want to calculate the displacement. So for instance, if for this question, you are asked to calculate the change of height at point A, what we would do is we define this virtual system, and in that system you apply a unit load. Again, it's a virtual load, it doesn't really exist, it's hypothetical or it's fictitious, exactly at point A and downwards. And that would give us a downward deflection, obviously. Now, basically what happens here is that we are using a concept that is fairly simple to understand. If you think of what we had previously, the internal energies that we had in the previous example, we had them from sum of, maybe with the 1/2, we had them with F times delta. Now, remember, in that example previously, the delta that we had was FL over EA, which is now exactly what we have here. But also in that example, the force was the same force. Now, the idea here is, if a system is in equilibrium and you apply a unit load, or you apply a virtual load, again, it could be a unit load or not, but if you apply a virtual load, a fictitious load, still, within all the other members of the system, you would introduce additional virtual forces that would also remain in equilibrium with that force that you just applied. And then again, the system is linear, so you can imagine if you apply a force 1 here, for instance, in this member, the force 1 there would result in an additional force n. Now, if you, instead of 1, if you apply 2, then it would result in 2n. If you apply 5, it would result in 5n. It's a linear system. So if you apply a virtual unit load or a virtual load, you would end up with virtual internal loads that would also result in equilibrium. And now, if for all those virtual internal loads, if you calculate their energies or the work that they do or the internal energies of all the internal forces, their internal energy must also be equal to the external energy that you applied. Okay, so basically this is still the same thing. Remember previously we just said UE equals UI. What we are saying now is that if you change that UE a little, so we call it delta UE, and we do that by adding a little force to UE somewhere, that should also be equal to the change of all the internal energies. This is exactly the idea. And that delta UI is exactly this. And this is exactly delta UE. So this is the change of external energy, or we call it virtual work. And this is the change of internal energies. But they must be also equal. Okay, in this formula, 1 is the external virtual load acting on the joint of interest in the same direction as delta. So you want delta downwards, you apply the force downwards. If you want something in the horizontal direction or the displacement in the horizontal direction, you apply the force in the horizontal direction. Delta is the joint displacement due to real loads. N is the internal virtual force due to virtual unit load 1. And as I mentioned, N is always proportional to that 1. So if instead of 1 you just call it F, it would still work. Now capital N is indicating the internal force due to real loads. We are going to learn this with an example together right now. Exercise 3 in this lecture is similar to problem 1411 on page 762. And the structure that you have in this problem is identical to the problem that we had previously, exactly with the same dimensions and force. But now the problem description has changed. Determine the vertical displacement of joint C. Of the truss structure shown in the figure, the cross-sectional area of each member is 400 millimeters squared and Young's modulus is 200 gigapascal. So it's exactly the same structure as we had previously, except that now I am asking you what is the change of height or deflection at point C, not point B. And as I mentioned previously, what we want to do now is to use the method of virtual forces. The first step is similar to what we had done before. Before we talk about the virtual system, we should talk about the real system, or we should solve the real system. So first you solve the real system and you calculate the forces, the internal forces within each member. Then what you do is that you apply a virtual force of 1 at point C in the same direction that you want. In this case, it's downwards. You apply this virtual force, and then for that virtual force that you apply, you calculate the internal virtual forces. So you would get a force of 1 in CD, that's tensile, so it has a plus sign, then minus 1.414, that's compressive, and you have 0 and 0. So these are internal virtual forces. So basically the forces that you see here, these are N's, internal virtual forces. And the forces that you see here, these are the capital N's, real forces or real internal forces. So what you want to do now is to just use this information in the formula that we have here. And in order to do that carefully and clearly, we draw the table again. We have our members AB, BC, AC, and CD. For each of them, now you see there is a new column here. There is this column that has small n, that's the virtual force. And then for clarity, I'm writing the dimensions also, or the units. So if we fill out the table, these n's, the capital N's are clear. These are the real loads. The lengths are clear. They are exactly the same as the previous example. The areas are identical, 400, and elastic modulus are also identical, and they are all 200. Now, the small n, the virtual forces, are 0 and 0 at AB and BC. Within AC, it's minus 1.414, and within CD is just 1. So if you calculate this relation n times NL over EA, basically by using each row's quantities, you would have 0, 0, 7.07, and 5. You add them up and you would have 12.07 Newton meter. So again, the dimension or the unit here is Newton meter. Now, this is what you had on the right hand side. On the left hand side, we have the virtual force, which is in kilonewton, times delta. Again, because the unit of the right hand side is Newton meter, if 1 is the kilonewton, or it has the dimension kilonewton, then delta should be in millimeters to be consistent. And that basically tells you that delta of point C is 12.07 millimeters downwards. And then again, it's downwards because you have a plus sign and you applied the force downwards. So it is in the same direction as the force that you apply. If it was minus, it would actually mean upward because the force you applied is downwards. All right, so this is exactly how you should use the formula or the method of virtual forces. We will just look into this again with another example just now. Exercise 4 and the last exercise of this lecture asks us to determine the vertical displacement of joint B in the truss structure shown in the figure. The cross-sectional area of each member is 1250 millimeters squared and Young's modulus is 200 gigapascal. So you have a triangular structure as shown in the figure. You apply a force 1 kilonewton here and you're asked to calculate the vertical displacement of joint B. So you can imagine, because you have a roller here and it's fixed here, you can imagine applying a force on B would maybe change the deformation like this. So you would expect it to come or to change the coordinates in the x direction, but also you would expect it to come down a little. We want to calculate that deflection. All right, so this is the picture basically with the dimensions that we have. As we mentioned previously, we split the problem into a real force problem and virtual force problem. For the real problem, where you have real forces, the force that you have, the real force you have is 1 kilonewton, and the internal real forces are like this. Again, you can calculate this from the method of joints or method of sections, but this is our usual truss structure example, so it's easy to calculate this. So this is our real forces. Then because you want to calculate the vertical displacement at point C, we apply at point B, the vertical displacement at point B, we apply a force of 1 kilonewton, or 1 again, at point B in the vertical direction. And then you calculate the internal virtual forces due to the 1, which are shown here. Again, you can imagine that from the two supports, you should get 1/2 each downwards due to symmetry. And then again, you can calculate the forces within each member from the method of joints that we had previously. So once you have these, all you need to do is to just use the formula that we learned for the method of virtual forces. And then again, here the ends, the capital N's correspond to the real system, and small n's, they correspond to the virtual system. If you draw the same table as we had previously and fill out the table based on the dimensions and quantities that we have calculated, then the sum of quantities on the right hand side are given. And by equating that with the left-hand side, you can calculate the vertical displacement of point B as minus 0.0027 millimeters. Now, pay attention. This is now a minus sign, but because we assumed the force that we applied was upwards, now minus sign in this example means downwards. In the previous example, if you remember, we had applied a force which was downwards, and in the previous example, plus meant downwards. So you should just pay attention to the sign here. Okay, in any case, this is the vertical displacement of point B, and we have just calculated it using the method of virtual forces or virtual work. All right, this was our lecture on energy methods. In particular, we covered sections 14.1 to 14.3, 14.5, and 14.6 of the book. That was our only lecture on chapter 14.